Welcome, everyone. Today, we have Professor Kostas Alexis to give a research talk on resilient robotic autonomy, methods and systems. Dr. Alexis is full professor at the Department of Engineering Cybernetics of the Norwegian University of Science and Technology. Highlights of his research include leading Team Cerebus, winning the DARPA Subterranean Challenge, and a host of contributions in the domain of resilient robotic autonomy, in perception, planning, and control, including learned navigation policies. His earlier research includes setting the endurance world record for UAVs in the below 50 kilograms class, with Atlantic Sola flying continuously for 81.5 hours. Since becoming professor, he has been the PI for a host of grants from NSF, DARPA, NASA, and many other awards. Professor Alexis, now I will give the floor to you, and now is your time.
Thank you. Thank you very much for the introduction, and thanks a lot for the invitation. And it actually feels great to be among colleagues that I know very well and like their work. So let me now jump directly into the topic of my talk. I'll try to talk to you about today what we try to define as resilient robotic autonomy, both in terms of architecture, but also some specific solutions that represent recent or relatively not so recent results of our work. But before that, let me actually just show a small video that is kind of a mashup of results, just to indicate that we want systems to be able to access, navigate, and conquer effectively a diverse set of very challenging environments. So here's a drone, flying in an underground tunnel. Here's a legged robot performing exploration in an underground tunnel. Then we can see the process of deploying 4 of such systems in an underground network of different facilities. We can see this drone flying through smoke and dust, navigating and exploring a nuclear power plant. Most of these results come from the DARPA Subterranean Challenge in any case. Exploring and inspecting a ballast water tank inside a ship, on the sides of a ship, so the ballast tank facilitates stability of the ship. The same drone exploring an underground abandoned mine, also somewhere in Norway, close to Trondheim, close to the university. And also a modification of the same drone navigating through a forest, eventually all of them with a goal of getting some sort of meaningful representation of the environment, understanding reason about it, and so on and so forth. So I think the key message I want to point out is that we care for autonomy that is deployable anywhere with very little preparation, if any. So the ultimate holy grail, of course, that everybody considers is the ability of enabling robotic systems to go at any place, in any condition, subject to any possible uncertainties and risk, and execute a mission with safety and reliability. Now, if we try to think about this in a general sense, then we ask the question, how can we have robotic systems of diverse robot configurations, not only flying, for example, not only ground? And what is the commonality between trying to develop autonomous solutions across diverse robotic systems in order to instill onto them reliability and resilience? And if we look at general studies about resilience, we will see that we are asked to instill into systems these 5 key properties, which is from the universal recovery, the ability to recover from an error, response to an error, response to a challenge, robustness against errors and challenges or uncertainties, and so on and so forth, redundancy in case of potential failure of any of its components, and resourcefulness, which is different than redundancy in the sense that it's not only necessarily replicating solutions, but also using your own resources in a different way in order to execute the mission to the best of your capacity, right? And at least ensure the safety of the system and the safety of the environment, of course, and of course, the maximum potential capability of executing the mission. Now, if we try to think how we can instill resilience, we should think of the general loops of robotic systems. And it is my main first view is that despite the great progress we have on data-driven methods, it is a very good idea to try to modularize the architecture of a robotic system in the sense that it is key to identify what are the specific components that have to be designed, what is the role of model-based or traditional methods, let's call them, or data-driven methods within each of them, and put them together in an architecture that makes sense in order to facilitate and prove, or at least demonstrate or verify with whatever means of verification this is most applicable, that the system will operate resiliently in any environment. I'm going to spend 2 or 3 minutes on a very simple diagram, right? Just to consider that, typically, if you come from a controls background, your view about the robotic system is typically something like this, right? There's a system, there's a control module, there's a planner, some perception module, which in the simplest case just performs basic state estimation. And of course, in the last years, people have also coined the idea that, well, we can just learn all of it in an end-to-end fashion. And in both cases, people are designing this given a robot from some designer, some company, and so on and so forth. So there's two limitations, first of all, in the core pipelines. One limitation that breaks everything into subcomponents perfectly and designs it given a certain robot. Another limitation that still uses certain robot design and tries to learn an end-to-end module. Of course, in reality, people are doing more like this at the moment. So they have several modules and they have models and learning into each of those. There is more interconnection between the modules and more back and forth communication between such modules. But I think the most important thing that we should be going eventually in the future is the potential of co-designing autonomy and embodiment, in the sense that if we also try to connect our research with a broader discussion about AI, I think the first core message I want to make today is that robots are embodied agents, and this is a distinct feature compared to just general AI agents. And in that sense, we should consider not only given a robotic system, what can we do for its autonomy, but could we potentially explore the co-design of robot embodiment and autonomy synthesis. Now, if we focus still on the lower part of that, I'm going to comment about this co-design just at the end of this talk. Then we should be thinking, what is this synergy of model-based design methods and data-driven learning? And of course, the best synergy is to be guided by the notion of performance and safety. And back to my comment of embodied agents. And I highlight again that we should not just treat them robotics as just application for other domains and perform best possible SLAM or best possible control and so on and so forth, but we should reflect on the specific needs of robotic autonomy and possibly what a robot design in terms of an airframe, for example, in terms of a legged robot, in terms of an underwater system, can assist in making autonomy more resilient. In other words, it is a good reflection to think that, for example, our body is very forgiving in potential errors of our autonomy, our ability to navigate. And what I'm going to try to talk today is this direction. How can we instill resilience into system control, planning, and perception? So let me now jump directly back into the modularized resilient autonomy architecture and try to go topic by topic, from multi-model perception to path planning, and then to policy learning, and eventually demonstrations from robotic systems. So when we say resilient perception in the view of our lab at the moment, the core things that we care is, first of all, obviously, we need to be able to operate without infrastructure support or other means of external estimation of the robot pose or any other part of the state. So we typically just say GPS denied, but this broadly means no infrastructure support. Sensor degraded in terms of presence of things such as self-similarity, darkness, obscurance, and so on and so forth that degrade the quality of the sensor data. Be able both to perform SLAM in these conditions, but also reason to the extent possible about the environment. Now, when we talk about SLAM, the classical thing that we have in mind, we had a lot in mind during the Darwin's Training Challenge was the ability to deal with very difficult conditions such as dust, smoke, and so on and so forth in underground mines, right? And we approach this in a multi-modal but loosely coupled approach where every modality, LiDAR, thermal, visible light vision, and so on and so forth, are fused together in a coarse-to-fine cascade architecture. And this, of course, allowed us to implement certain things in a computationally very efficient fashion. And in that sense, for example, we could have the obvious example of a system that is deployed in a self-similar tunnel, but due to the fusion of LiDAR in combination with visual cues alongside IMU, we had correct estimation of the scale of the environment despite the otherwise self-similarity that would render a LiDAR-only method brittle and most likely failing in these conditions. Now, that on its own, of course, it's a good result, but we should think more generally, how can we design a general architecture, which we call in our lab at the moment Mimosa, to be able to incorporate any possible modality and kind of lead essentially the problem into some sort of general software package that can afford the integration of any sensor, LiDAR, vision, thermal vision, radar, and so on and so forth, and accordingly be able to fuse this data towards estimating the robot pose and the map of the environment. In that sense, we believe that factor graphs is a more applicable tool in order to be able to incorporate the relevant formulation in a flexible fashion. And it allows, of course, to do calculations that deal both with short-term associations, but also with mid-term and long-term associations. Estimate the robot pose, include constraints that come from different modalities, from vision, from IMU, from LiDAR, and so on and so forth, in distinct ways, but it allows to incorporate constraints from any such modality. Importantly, it allows us to deal also with modalities that come at very diverse and possibly not perfectly synchronized timestamps, which is a possibility, although suboptimal, it's still something that can happen on a robotic system. It allows us to operate on different spatiotemporal scales through a fixed lag estimator in combination with a full pose graph and how this can run on multiple architectures, or possibly on 2 different levels. It allows us to deal with the possibility of a constraint coming in the future and being found later that is ill-conditioned due to, for example, geometric self-similarity, and be able to connect and disconnect constraints from the optimization. And it allows us to deal with detecting short-term degeneracies, for example, by tracking the eigenvalues of the underlying optimization on LiDAR registration, or long-term degeneracies, which then will mean that we have the ability to reformulate the graph back in time and then use the reformulated graph for the estimation of the results of the robot pose and slant overall future in time, which means that effectively we are changing how the Markov process evolved over time, because we identified later in time that some of our estimation earlier was wrong, right? And we need this ability to dynamically reformulate the graph in order to be able to correct future errors for ill conditions that were detected later in time. Now, if we put this in results form, then we see here in a test where animal is walking inside an underground tunnel, and we are fusing visible light data and LiDAR data. On the left, previous method from ours, couldn't manage the particular degeneracy. On the right, this particular method. Here, we're fusing thermal data and LiDAR data, and we have simulated artificial loss of LiDAR data. And of course, we can maintain reliable localization mapping under such conditions. I think this is currently something that is, I would say, well established in the state of the art. Next to all teams in DARPA Subterranean Challenge provided some solution of that nature. So I think this is something that we want to keep building further in order to make it effectively a tool that can incorporate any such modality. Any such modality, either this comes directly with traditional methods for incorporating and assimilating relevant sensor data with traditional registration techniques and so on and so forth, or for example, by improving how sensor data can be incorporated through possibly learned methods. Here, an underwater test for learned stereo depth that incorporates odometry priors. Again, the idea of combining learned methods with traditional techniques. The odometry priors incorporated in order to use the previous point cloud and the odometry update to predict how the future point cloud would look like, and then for initialize and optimize an optimization problem to converge faster and more accurate to the solution of what is the current depth. I go through many topics in this talk because I would like to present our overall architecture for resilient autonomy. But the key takeaway from the previous slides is that we want to have a solution that's able to deliver at least the ability to know where you are in the map of the environment, subject to any condition, and the solution to that is primarily multimodality. I haven't yet commented anything about understanding the environment, semantics, and so on and so forth. I would like to do this as part of this section about resilient planning. Now, in path planning, it is very common to solve single objectives such as exploration, coverage, path planning, and so on and so forth. Now, at the same time, it's quite obvious that the robotic system that's going to be deployed on a very complex, let's say, industrial environment, it is very unlikely to be expected to execute only a single task unless it is a highly tailored, highly human-driven, highly supervised process. But if we care for really autonomous systems, we first care for multi-objective, multi-hypothesis optimization. And the second key observation I want to make from the beginning is that should think of planning in two ways: on some sort of relatively mid and long-term scale, on a very low, so on a very local, short scale, on a very local scale, where we want the robot to be able to make adaptive change of its viewpoints in order to observe and gather information and pick the best information from the environment. I will comment about this a few slides later. On the more traditional front, this slide represents, for example, how our methodology worked for the exploration of the DARPA subterranean environments. And we have kept expanding upon this methodology, and we have deployed across very different environments, and I will give some examples afterwards. But the key elements of the architecture involve a local stage where the system is going to optimize some sort of information gain, for example, exploration. That was what we developed back then, but now we have extended among several different other formulations of information gain. It's going to perform collision checking. It's going to also respect constraints of traversability. If it's a ground robot, it's going to observe the constraints of, is there a ground for the robot not to fall? If it's potentially going to negotiate a cliff, it has to go close to the cliff, but not really fall into the cliff, and so on and so forth. It's going to be able to adaptively scale the density of the graph based on the computational capabilities, and so on and so forth. It's going to exploit ESDF, TSDF formulations in order to be able to do fast collision checking, and so on and so forth. And one could pick a different formulation for the representation of the environment, but that's the one we are picking from our side. And at the global scale, it's going to be memorizing a very sparse and adaptively sparsifiable graph that will allow us to know where to reposition, not in the classical sense of the frontiers as we are accustomed, but also to identify which vertices of a previously visited global graph are interesting as pathways to new information gain, right? So this, for example, could be an intersection in a tunnel. It doesn't have to be, strictly speaking, a particular frontier. And I mentioned some of the key features also, and it's important to highlight that a core element for this to work efficiently is the computationally fast representation of the environment for tasks such as collision checking and so on and so forth. And here we are using a method released from ETH called Poclus. Now, this particular line of work was deployed identically both to ground and flying robots. And since then, we have deployed on a host of different robot implementations, again, both on ground and flying. And here you see a 37-minute exploration of an underground iron mine in Switzerland with Animal. And this was actually a few months before our team went to Kentucky for the Tartan Challenge finals. Now, at this point, what is key to understand for the mission, otherwise it just looks boring, is that the robot will perform multiple times this relocation process in order to be able to reposition itself to interesting areas of the environment that are pathways for gathering more information again before returning home. And then at return home, there will be a flying robot that will actually execute the remaining of the exploration of the same area of interest. I'm not going to play the full video. It's relatively long. But at this point, for example, the flying robot is exploring its own path in the environment. Now, I mentioned that it's important to reason, not only to just explore or inspect, right? And reasoning for certain objects of interest in the environment is also some means of compression. If I go into a very large scale setting, but I only care for particular structures, for example, for some industrial inspection application, I not only have means to just focus my attention more, but I also have means to compress the information I really need to store. So we're going to this direction of semantically driven planning, both in what is presented in the slide, which is that the robot detects semantic of interest, and then will execute some specific modes in order to make sure the mesh is covered fully, there's no hole, the mesh is covered in full resolution, and so on and so forth, but also by means of only storing this particular information in order to be able to adaptively reconstruct models of the environment at desirable levels of resolution, not in a uniform sense, like I want to cover, an environment with this size of voxel or this type of mesh, but focus on the particular entities of interest. Now, some results from previous work on that, we're going to be presenting this also very soon, and we plan to make an open source release along this line again. We are demonstrating that naturally, the moment you inform a planner for the particular notion of semantics or objects of interest and how should they be inspected in any particular way that you have in mind, you can have not only just a small increase compared to previous methods that disregard this type of information, but a significant increase because naturally the method is more informed about them. And it is key to also note that in most cases, in industry, for example, the semantics of interest are particularly sparse in the environment, so we can actually heavily exploit this. We can take this now and go to very different environments compared to, for example, the Tartan Challenge, enter the ballast tanks of a ship, and here we deploy the robot. It's actually exactly fitting the access hatch of ballast tanks, and we can get it to explore these environments, provide maps for us. And here you see, for example, the results where the system is conducting a process that bifurcates between two behaviors: an exploration behavior, which just makes sure that there is volumetric coverage, so the LiDAR has seen everything in the scene, and at the same time, visual inspection, where the system switches, this is what's executing now, makes paths that look all around with certain resolution guarantees and also incidence angle guarantees in the environment. It's going to execute this over several sections of this ballast tank compartment. Now, ballast tanks are rarely as large as you see in this particular setting, which is kind of spacious and so on and so forth, and we just have to go through very large doors, let's say. Most likely, ballast tanks look also something like this, and the pear-shaped manhole that you see there is 0.7 by 0.5 meters in size, and the robot is roughly 0.4 meters in width, right? So it is key to be able to have a system that it makes actually a small bump due to some small error in Z, but without any particular problematic effect of the system. It is key to have a methodology that's able to scale across environments that can be, in principle, very large in overall scale. An actual FPSO vessel, for example, is hundreds of meters. Multiple hundreds of meters of such ballast tanks inside, but at the same time has to be able to negotiate particularly narrow cross-section access pathways and so on and so forth, right? So we need the semantics, not only to know what to expect, but also the semantics as a way to identify how we navigate better such type of environments. And this is also we have this terminology, inspection semantics and navigation semantics. And we're using the manhole detection here as a navigation semantic to drive the particular exploration process of this zone. Now, resilience and reliability also means that you can take the same method and apply very little to no change and deploy it in a vastly different environment. So we are here actually last week in some field tests in Helsinki or outside of Helsinki in Finland. And we're deploying this exploration method in order to be able to negotiate and navigate and explore and map a forest there. And it's quite notable that it's a forest that's highly dense and with many sticky branches, which represent very difficult obstacles to in order to detect them and therefore be able to avoid them in the volumetric map. Nonetheless, the method worked to our surprise, actually, or not necessarily, but anyway, in a good sense, surprise, worked reasonably well in this environment. Well, the thing that we couldn't do much is to go faster for the purpose that it was never really designed or tested or tuned for any such environment. But even without any tuning, it was able to provide reasonable results. Now, if these two lines of work give us resilience in how we perceive the world and how we map the world, and also how we plan actions, for example, to inspect and cover or otherwise reason about the world, then one tradition should say, okay, now the only thing I need to do is take these commands and deploy them in a controller. And indeed, this is what we did up to now. And the formulation that you see here is very old, comes from times that, I was also doing my PhD and later my postdoc at ETH, but that's something that's quite standard currently in the community, to implement some sort of MPC for a flying robot. And you can use also any other type of control if this is your preference. There are some good benefits. For example, here the robot has lost a propeller, it keeps overall XY authority, but otherwise it uses Go. But I would like to depart from this, and we try to depart from this idea that you're going to have this classical approach of splitting everything into modules perfectly, and try to think of control as three things. As a way to fly or go to a particular destination, that's a classical approach. It's a way to avoid obstacles, anyway, ensure constraints, but these constraints not only in the classical sense of some very well-defined state and input constraints, but constraints generally in the environment. So, for example, for us, avoiding obstacles or other constraints as traversability for a ground robot, for example. And the second, this is the second thing. And the third thing would be as a methodology to gather at very local, very short spatio-temporal levels, the information necessary to be able to plan all your other actions, to be able to get better data for your SLAM system, to be able to get better information for semantic reasoning, to be able to eventually plan better paths for inspection, exploration, navigation, traversal, or possibly for a different type of robot manipulation tasks. So we try to create kind of let's call it a super module that is a control policy that will not rely on the necessity to have maps. We don't want to replace the need to have maps. We want to have maps. We want to be able to exploit onboard SLAM and so on and so forth. But we also need to be able to have a system that is ready to work even when traditional SLAM, for example, might fail. The second is that in line with the first, we don't necessarily require position feedback. So long as we have it, we exploit it, but we shouldn't require necessarily that this is consistent. Accordingly, we also say that we shouldn't require that we have a consistent online mapping. We should be able to act on real time or a short period window of real-time sensor observations. We should be able to evaluate if a certain action, of course, is collision-free with what like, account for uncertainty both on the robot partial state, so it doesn't include, for example, position, but also on epistemic errors on our understanding about essentially the network itself and how the network has been trained in the environment, and offer attentive navigation. As it goes to a desired destination, be able to sample the information that's necessary. This has roots into core ideas about, for example, the human navigation, or most of the animals' navigation system, whereas the idea of visual silence, where the robot navigates, or the agent navigates on the robot, and navigates, and as it navigates, samples the best or the most appropriate information from the environment, both from a bottom-up and from a top-down perspective. If we put this in a very simple block diagram, it will look something like this, right? Let's say our sensor input is some depth image. And also on the same depth image, we are able to identify a mask, which comes, for example, from visual silencing, from an explicit detector of an object, and so on and so forth, that represents the areas of interest. Then we have the robot partial state, which, for example, should involve, in this particular work from ours, the linear velocities, the angular velocity around the z-axis, and the rolling pitch angles. And of course, some goal vector, which we calculate real-time based on position feedback when this is working. But otherwise, even when position feedback is highly drifted, then you should be able to at least point us in the roughly correct direction. Then we want to have this navigation policy that is able to spit out the control actions to follow that should be commanding a low-level controller that's going to execute, for example, roll and pitch commands and thrust command for a multi-rotor, for example, and be able to replace essentially traditional position control by simultaneously also offering the ability to be resilient against significant, very long-term failures and slump, number one, and number two, offer the possibility to attend into particular viewpoints and areas of interest. Now, that's the architecture, the particular architecture of this method. We call it Oracle, and it assimilates a depth image or a sequence of depth images eventually. The robust partial state, it has a motion primitives library. It's going to be a collision prediction network that's going to identify which of these possible actions are collision-free. And I'm going to show also an extension of this to account for information gain. Now, eventually, this is going to involve a layer that is going to be compressing the depth image and going to go to increasingly lower and lower dimensions of the depth image originally. Then it's going to this be combined with the robust partial state. And instead of taking on the mean of the robust partial state, we're also going to get the uncertainty into account. And for that, we're going to use the uncertainty transform. So we're going to get sigma points for the uncertainty over the partial state. We're going to get an LSTM, so a recurrent network, in order to be able to deal better with how we predict the effect of a certain action and train this methodology. But instead of training a single network, we're going to train also an ensemble of such collision prediction networks in order to be able to deal better with the epistemic uncertainty of the process, while the aleatoric uncertainty is mostly related to the uncertainty over the robust partial state, right? So therefore, we take the covariance into account and we take the sigma points over the covariance in order to be able to account for them. And we're going to get the motion primitives, and the motion primitives will be represented for us in 3D velocity space. So we're going to be commanding velocities for the robot. And as mentioned, it's going to be a component that deals with the aleatoric uncertainty over the robot's uncertain partial state, a component that deals with the epistemic uncertainty through a deep ensemble of collision prediction networks. And especially this relates to how we best handle cases of weak input data. And I guess you're most of you familiar with problems such as, for example, getting very accurate depth point clouds around certain small objects. If the object is very thin, it's very difficult to get actually a good reconstruction of that. In the forest, this was actually, to a certain extent, a total mess. There are problems with areas that are reflective or objects that are reflective and a sequence of relevant challenges that exist all around. Now we can take this and we can use the deep ensemble to calculate essentially over the ensemble the best possible cause formulation that characterizes how likely a certain motion primitive is to collide or not with the environment. And from the list of motion primitives that are above a certain threshold, take the one that gets us to the desired destination. Now, if we're able to do that and we're able to negotiate the environment in terms of safety, then we're also able to incorporate potentially information into the collision prediction network or into a parallel loop alongside the collision prediction network that relates to the visual importance of areas of interest. So the figure that you see here comes from work that is much older. It was about a visually salience-driven exploration plan that, as it was exploring, was also pointing the attention of the robot to areas that are visually attentive. Visual salience is a model of how, a model of the attentive mechanism of the human eye. To the extent of that this is successful or not, there are some questions if it's really a bottom-up or only bottom-up process, but nonetheless, there are several methods about this. Now, this work just wanted to say that you give me a mask, essentially, over the image, and then I'm able, as I explore, to point also the robot's attention to the areas of interest. Now, we can take this general principle, feed it back to the previous method, as I mentioned, forget the need for map and so on and so forth, and use this mask associated with a depth image and train an information gain network that uses an expert that truly knows how a certain viewpoint gathers in the future information about the area of interest. We do this in simulation, of course. And accordingly, this information prediction network can spit out a prediction of the information value of any of these motion primitives that I mentioned before. Now, within these motion primitives, we can take the one that is safe and simultaneously offering as much as possible from the information gain as mentioned. So let's see some experimental results. Here, the robot will take off. It's going to be flying with 2.5 meters per second. Remember, there is no position feedback in what you see. There is no map of the environment taking place at any point in time. And the robot will navigate the setting and will avoid the obstacles in its environment with good success. Now, if we take also the same thing and we deploy the robot not only with the goal of collision avoidance, but also to attend the objects that you see here, which we give them mask by running some object detector, we can fly. The robot will look towards the area of interest. After it comes within its view, so it's going to make a small adjustment of its viewpoint. while it keeps going towards the desired destination. And it's also key to mention that this particular result, actually, the velocity estimation failed miserably, but it's key that the method does not necessitate that even the velocity estimation is reliable, right? So it only necessitates that you have a good model of your uncertainty. And just keep using the forest as an example of transferability and resilience in very diverse and very different conditions. This is, again, from the same results last week, where the same method that was never deployed before really on forest data, other than 1 week before actually we went to Finland for performing this test as part of the project, is able to negotiate reasonably well this dense forest that you see here, right, with multiple forests per square meter, for example, of a forest area. Now, however, you could criticize that there's nothing modular in that, right? So here we trained an end-to-end policy. So we reflected upon this, and we thought that the greatest limitation of training this policy end-to-end is that although we can get relatively easily data that present the problems of real sensors, we have no way to model them in very high fidelity simulation, or it will be excessively difficult to model all the problems of real sensors in simulation. So although we can get easily data of real environments, we have no way to assimilate them in this training process. Therefore, we actually remodularized, we redesigned this pipeline and modularized a first step, which allows us to train a semantically enhanced variation autoencoder that compresses latent space, and this latent space will be used alongside the robust partial state to otherwise perform the process that I described for collision-aware navigation as a control policy that runs at very high update rate. So by the way, these methods run at 20 Hertz, for example, on your onboard computer on the small drones that you see from our side. So these drones, all of them are between 1.2 to 1.5 kilos in total weight, including all sensors, batteries, and so on and so forth. Now, the semantically driven variational encoder aims to say that if we know that certain entities are harder to reconstruct because they are lossy, because there are gaps in data, and so on and so forth, for example, a reflective small surface, a very thin, narrow branch, and so on and so forth, then we can incorporate relevant mass, possibly in simulation, but also to a certain extent on some small amount from real data, and be able to guide the semantic reconstruction loss of the VAE such that these semantic areas are better reconstructed in the otherwise highly reduced dimensional space. And the other thing that wants to say is that as long as collision avoidance is concerned, big objects do not have to be represented and reconstructed accurately. So we don't care for how visually appealing the reconstruction is. We care if this reconstruction is good for the task of collision avoidance, right? So it is key that if I have a very big table, the only thing I need to know is the general dimensions of it, right? I don't really have to have high fidelity on how acute are the lines of the table and so on and so forth, if the only thing I want to do is to avoid it. So we go, for example, on this architecture from the depth resolution of a classical depth camera, let's say 228 variables, which are then fed into the collision prediction network. So a great reduction on input dimensionality. And this is some results that you see, and we, of course, demonstrate that, if you were to use traditional methods, you wouldn't be able to, for example, with FFT, right? You wouldn't be able to reconstruct this properly at the reduced dimensionality as reduced as the semantical enhanced VAE. Just traditional VAE, of course, will also fail because it doesn't pay particular attention to the difficult to reconstruct objects of interest, and the semantically enhanced VAE actually managed to do exactly that. So if we deploy this now on the robot, and the result that you see here, again, the system does not perform SLAM, does not have the position estimate of itself, and so on and so forth, has the attitude estimation, because attitude estimation for flying robots is relatively easy to have actually, and it's able to negotiate the navigation within this packed environment that also involves some what we call thin obstacles. Now, this one really thin was 4.8 centimeters. In the next part of the video, this is going to be up to 2.5 centimeters in width. And another key factor is because we are able to run this increasingly faster as GPU availability on board increases. I believe it's not going to be by any means far away to run this up to 50 or even more hertz, which means we can run these prediction loops very fast, run these inference loops very fast, and eventually achieve faster and better control, including collision avoidance, which allows us to also mitigate some risk on the path level. And again, just as a test, we took this again back to the forest, this modified method. And again, it was able to negotiate this particular dense forest reasonably well. The only, for those of you that do field robotics, you might notice there's some duct tape on the system. The only problem we had was that our main estimation for visual and getting the velocity of the robot was pointing somehow up, because this robot was always made to consider underground environments. And of course, pointing up towards the sun is not the best thing. So that was the only thing really that took quite some time to fix in the field test. Since I mentioned about field tests, I want to highlight, as coming into conclusions, the great importance of field results. And I think as a personal statement, it's not only because we just can see and evaluate the results, right? For me, the most fruitful process of doing field testing is that we see things that we actually didn't necessarily expect in our lab evaluations, and often essentially enhance our research agenda for a good amount of time future. Now, what you see here is the Cerberus field testing regime from 2018 to 2021. That was a highly international team with colleagues from the US and Europe, including Switzerland, in the UK, and so on and so forth, and several entities also in the US. Myself also moved from the US to Norway during the execution of the project. And therefore, you see many tests in many places. These are instances, but I'm going to play this video. First of all, it's hard to see it possibly it's a 60-minute video compressed in 2 minutes. So I think that's hard to somebody to pay attention to what's going on. But in any way, it's available, and it's also kind of old news. The competition from DARPA ended in September 2021. But this was the deployment back then, and a team of robotic systems has been deployed and allowed us to go on to win the competition. This here is actually a better understanding of the data. All these videos are also online, so if somebody has interest, you can have a look. We show all the paths from the robots as they were taking place, and we also show how, when, and what artifact each of them detected, and how and in what position exactly it detected in order to be able to get the score. From the DARPA Subterranean Challenge, for those of you that may not be familiar, this involved detecting certain objects of interest with predefined classes and find the correct class, and also record it within 5 meters of absolute error compared to DARPA ground truth. And this is, for example, the final map from our side, and where we detected the particular objects of interest that I mentioned, allowed us to get score. A very fruitful experience, not only just for winning it. I think it will be fruitful in any case, even we're first, second, third, or whatever. Very fruitful because it was a very good case of combining new research from our side with a very demanding process of the competition, right? That something should work now. And it was a decision that we took in our team very early on. Should we try to look away from our core research agendas, which, as long as the main partners of the team, this involved legged and flying robots and autonomy, very little effort on communications and so on and so forth? Or should we just focus on our core research? And for us, this eventually played out fantastically. So that's also my core message, that one can approach this competition by still focusing on the core research progress one has in mind, and then try to embed these new results into the competition readiness. Also allowed us to get, the good prize reward after winning the competition, $2 billion, and a license recognition from the US Senate. And before I close, I just want to highlight a couple of things in terms of both what we consider a good lab, but also some ideas for the future. Here's an idea of what we consider a good lab. So this is a process that is, kind of integratory process. I think this is type of things that we do because they're cool and because robotics are cool. So, nobody necessarily required a legged robot that deploys a flying robot, but some things of that nature are cool. Some things in robotics can be very useful, and we haven't achieved their deployability so far to the extent necessary. This is a robot that just demonstrates the ability to do nuclearized mapping and be able to characterize radiation and also identify isotopes of interest and so on. Now, this is happening to a certain extent. In recent, for example, Liability had a deployment in some DOE facility in the US, but this should happen much more, right? Because robots are ideal still to take a host of relevant applications that we don't want to send humans, and also ideal to be able to take a host of applications alongside humans, for example, in industry. We can do things that are, again, nobody asked just because they're very interesting. Here it's a connected multi-robot system, so two quadrotors connected with each other that perform a manipulation task. But the underlying math of control is very beautiful here, and the stability proofs, all these things are very valuable to do in the process of conducting a PhD, and the lessons learned are transferable, even if this particular system is not the one that industry will be using, for example, in the future. And before I close, I would like to just explain one picture from a summary of where things will be going for us in the upcoming future. We're going to be trying to investigate the possibility of this co-design between embodiment and autonomy. And I think this idea is quite old, actually, and people have coined this through evolutionary design and so on and so forth. But I think the key observation for today is that we can remove the rate limiter of designing a controller for automatically generated embodiments. And the rate limiter was that we didn't have the success in, for example, auto training, RL or otherwise, anyway, not necessarily responsible learning, otherwise learned controllers. But now we have great success in learning a control policy, including collision avoidance tasks and so on and so forth, at very high rates, and potentially on par with generating new variations of a certain robot class, right? So let's say we're considering, should we be using quadrotor for any type of environment, as we tend to do nowadays, right? Should we be using quadrotors plus rotorcrafts and so on and so forth, which essentially means that up to 2023, if we just look at the drone domain alone, we are mostly using miniaturizations of traditional aerospace designs. Now, there is work on biomimetic, but that follows another paradigm, which is I'm going to copy what we see in nature. We could think, however, that we could design optimized machines in terms of their autonomy functionality, their autonomy capabilities for certain class of environments. And if we were to do this for two very distinct types of environments, for example, let's say we take a natural forest or we take an underground cave, the resulting optimization for both the robot body and the robot autonomy should be very distinct, right? Should be having fundamentally very different types of robots. So we've been working along these ideas. And I want to mention that so long as something works, we try to put it in open source at whatever rate we can based on our own time availability. This is our current team, and we're going to be hiring roughly 10 people, PhDs and postdocs over the next months. A lot of them will be working on this idea I coined before on the co-optimization between robot body and autonomy. So if you are interested, please contact us. And with that, I want to thank you. I want to also credit my team for the work and the results that you see here. And I'm glad to take your questions.
Hey, yeah, thank you for the great talk. So now we'll receive questions both on Zoom and YouTube. So for those who are on the Zoom, if you have any questions, please raise your hands, or there's a Q&A chat functions you can use. As for the people on the YouTube, you could, if you share your questions on the chat, we'll pass them to the professor. Yeah. Yeah, please take some time to raise any questions. Yeah, please use the raise hand or Q&A chat functions here in the Zoom. Well, for the first question, before some others can ask questions, I might ask my first questions. Okay. Yep. So yeah, I have questions on semantically driven planning part of your research. But before the actual question on the semantic driven planning, like I'm a little bit confused about the term semantics here. Like I guess the term semantics are the semantics that we use in the computer vision, like computer semantic segmentations, and you're referring to semantic segmentations of the point cloud data. My question is, like, what are some examples of semantic class that you're referring to semantic in this work, and how is the semantic segmentation model being pre-trained before the launch of the robots? That's my first question on semantic driven planning.
Yeah. So I'll take the opportunity to discuss both what we do now and what we try to do in the future, and we'll hope to be able to present it very soon. So the traditional paradigm, as you say, is that we perform some sort of instance segmentation. We get segmented labels over the point cloud, and we can use those in order to be able to do inspection. And this is what our publications so far also do. Okay, so we get essentially this colorization essentially of the point cloud, and we say that these areas represent a certain semantic of interest, certain object of interest, and then we have some modified of the inspect function behavior. Now, I think it's good, and the publications are presented and so on and so forth, but that's not necessarily extremely powerful. I think what is powerful is the following. There is a host of facilities where if you see some instances of specific semantics, then you should be able to infer the distribution of these semantics in areas that you have not seen yet. So, for example, you are working in university corridors, right? So, in principle, a door could appear randomly in some place, but that's extremely unlikely to happen. Now, if you go to industries, for example, in the ballast tanks that I showed, and we work with industry in this domain, and we know very well, the web frames, the main structural components that keep this together, are actually pre-specified identically spaced with each other. So, as long as you see a few, then this is going to be the same across the ship. So even if you don't have this information a priori, a robot that executes a mission in the first minute, it should be able to get this information for the remaining of its mission. Now, why is this important? It is not important if you were able to spend 3 hours down there and execute all the mission with all the privilege of time. but it is important if you want the mission to be able to implement it at high speed, because that's the only way. Otherwise, time-constrained system should be able to do a long-scale exploration mission, long-scale exploration inspection mission. So the core thing we are trying to work at the moment is inference regarding the potential future positions and classes of semantics based on our current observation of semantics. But up to now, up to the published work that you saw in the results, indeed, we're using segmentation of the point cloud and inspecting given this information in order to be able to best match, best cover the mesh, best observe with other sensors, and so on.
Yeah, thank you for your answer. Then could you explain a little bit more about the difference between like semantic? There's a whole coverage phase and inspection phase in the semantic driven planning, right?
So you're referring to the particular work there. Indeed, I can go back. So here, essentially, what this I will say this is an observation that one can kind of have in most cases of reconstruction, right? So the traditional approach of saying that have we perceived something, in terms of coverage, is that we are using some representation, which typically is not extremely high resolution for the overall environment. And we say, yes, our sensors saw this area or didn't see. So for example, you can use a voxel map, right? And say, I perceived this area or I didn't perceive this area. And you can just colorize every voxel with perceiving this or not. Nonetheless, this doesn't mean necessarily that your mesh reconstruction, and depending also on the algorithm you're using for meshing, is going to be fine detailed in any particular section of the mesh. And you can have problems with detail, and you can have also complete holes on the mesh simply out of the meshing process. So the first thing we want to make sure is if we want to reconstruct the digital twin of the environment, we don't want the robot to come back with some data, with some problems, and then imagine we deploy a second mission. We have discussed with industry and people that use, for example, drones to manually go and collect digital twins, and they have reported this problem multiple times. Right? So first, we wanted to make sure that the robot, when it comes back, although the overall environment has not been captured perfectly, in the areas of the semantics, everything has been captured up to the level that there is no hole in the mesh, and all facets of the mesh are of certain resolution in terms of the observation. So these are the two modes that you see afterwards: semantic hole coverage and semantic inspection.
I see. Okay. Yeah. Thank you for your answer. Does anyone have on Zoom or YouTube have questions? I'm not seeing any questions on YouTube or Zoom. So, yeah, I have another questions on the actual deployments of robots in the scenarios like DARPA safety challenges, like or any other real robot experiments. Like, first question is, what are some challenges that you encountered when there's a big gap between simulations and field testing results, like both in planning and control side of your research? My second question is about the like multi-robot or heterogeneous robot scenarios, because in DARPA safety challenge we use like many different robots, like robots as well as drones at the same time simultaneously. So what are like just some challenges that you consider while you're deploying heterogeneous robots as well as multi-robots, and what are some like if we extend this, for example, semantically driven planning to, for example, multi-robot perspectives, what could be the challenges?
Yeah. So, I mean, many questions. I'm going to try to answer them as quickly as possible. So, your first question, right, about the generally called sim to real gap. I remember them. Don't worry.
Yeah.
So, about the generally called sim to real gap. Well, I think there are two aspects in it. The first is, are you using a neural net or anyway data-driven method or not? Now, before we discuss the need to train on data, I will say that generally speaking, in my experience, path planning in particular seems to be the one domain of research that you can do a lot of good results in simulation, and they transfer very well in practice.
I see.
So long as you have nailed down the environmental presentation, right? So long as this works and what you have in simulation matches what you have in reality, in my experience, you can do most of your work in simulation and expect a very good transfer in the real world. Now, this doesn't work out at all, of course, for perception tasks. So there you really need to have realistic data. Otherwise, the process of simulating realistic data might be unbearably more difficult compared to gathering real data. So for example, we are working now on underwater vision, right? It's so much more complex to simulate all conditions of underwater vision than collecting data from with an underwater camera, right? So of course, in principle, you need both, but the value of real data there is paramount. So we actually absolutely need it. Now, in control, I would say this depends on the system, right? So if it involves no contact with environment and so on and so forth, models are reasonably good. If it involves complex interface of contact and so on and so forth, then you also need potentially some real data. Now, the whole thing changes completely when we refer to learned method, data-driven methods, right? And then about the sim to real gap, my main point at the moment, at least, seems to be that if we can modularize it and take the most difficult to transfer part, so typically, for example, vision or depth and so on and so forth, and modularize it so that we also train together with real data, then this modularized approach allows us to somehow simplify the process of this otherwise end-to-end learning pipeline. So this is, I would say, I give this with a pitch of uncertainty. We are still to see highly reliable solutions of that nature being deployed in practice. But from the results that we have seen from the research community and also from our work, it seems that as long as you do modularization, you have quite high transferability in the real world.
I see. Okay. Thanks. Yep. Yeah. And my second question was on like deploying multi-robot and heterogeneous robot scenarios. The challenges.
Yeah. So I actually about multi-robot, I think this is simultaneously a very large challenge and a challenge that can be approached very differently if you have some sort of global knowledge, right? The whole idea of what is a multi-robot team comes to the question: is this the decentralized process or is it not? If it is not a decentralized process, and by decentralized, I mean both decentralized command, but decentralized communication also. So if an agent only really knows what's going on its own data, and is not allowed to connect and get information from the other agents, I think that's a generally very difficult problem, right? And it might be okay if we're doing basic things such as swarming and so on and so forth, and there are very good proofs for control methods that allow you to do swarming in a fully decentralized fashion and so on and so forth. But it can be very complex if we're doing things such as, okay, I'm entering an unknown environment, I'm going to be exploring in the best way possible, right? So we need to be able to share some form of data, and we need to be able to at least share in some sparse occasions. So if we're talking for this general setting, decentralized multi-robot teams, I think will necessarily remain relatively a hard problem. If, however, we are talking for the possibility that you can share information among, I would say this is more of a scalability problem. And the only real reason I believe we don't see multi-robot teams effectively so far is because no one is really asking them in practice, right? So we are still trying to make one robot work very well. And I believe if we make one robot work very well and very resiliently, then the aspect of scaling is difficult. I don't want to neglect it, but I think it all becomes way simpler if the individual machine never fails.
Okay, cool. Yeah, thank you so much.
Thank you.
Yeah, does anyone have questions? Yeah, there's one question from YouTube. I'll just read it. Hi, thanks for your great seminar. I tried and read your former works, including graph-based planner, motion primitive-based planner, RH and VP, and etc. Among them, I found you usually used Octomap and Vox blocks, which are quite slow to update and calculate the frontier region, and hence degenerate the speed of the algorithm.
I think he's absolutely right to a certain extent, right? So if the question somehow points to if we should something different, or that's the question?
Actually, he's still typing a question, okay. So yeah, but he's talking about your previous works in graph-based planner and talking about Autonomy. I'll just copy this as well on the chat on Zoom.
While do you have any comes,
the final comment is, do you have any plan to develop other mapping algorithms to resolve this bottleneck?
Right. So I think I would like to comment that our main first of all, I'm aware of works that employ different methodologies to represent the environment, and there are potential very good benefits. So I'm aware of works that use Gaussian mixture modules and so on and so forth, right? Instead of using representations such as Autonomy and VoxBlocks and so on and so forth. Now, in terms of speed up, you can also do a lot of things to speed it up. And, there are implementations on GPU and so on and so forth. But the most important change we are doing at the moment is that I'm also revisiting. For example, if we see the NBVP work, back then we proposed that we are solving in one optimization step, the exploration process and the collision-free process. And it appeared to be the most applicable idea at the time. But actually now with progress we have on learned control methods, where we can incorporate also the ability for collision avoidance, I believe the task of collision avoidance to 90% should be undertaken by control on its own, so by a control policy. And then this relaxes greatly the task the path planner has to do. It should still be able to identify collision-free directions and so on and so forth, but the low-level, very dense, spatiotemporal decision-making of how to avoid an obstacle should be left on the control policy, which then this means that the planner can be planning viewpoints or tasks and so on and so forth much more opportunistically in the environment and also potentially undertake some risks. I think the most limiting idea of all the work such as ours and also frontier-based exploration and so on and so forth is that all the decisions are within the explored space, which means that the robot is very conservatively trying to explore further in the environment. It is necessary to be able to make decisions that attempt to infer how the environment will be in the future, and then assign a control policy to go in this direction, so long as you believe and you trust that this is going to be collision-free and safe in terms of all the constraints of the system. So we will try to depend less and less and less on methods such as VoxBlocks, Octomap, and so on and so forth, or any other type of global environment representation for things such as collision avoidance.
Great. Oh, thank you for the answers. Do you have any other questions, both on Zoom or YouTube? Yeah, if there's no further questions, we'll wrap up today's talk here. And yeah, thank you again so much for the great talk, wonderful talk, and answering many questions. And thank you so much for just joining our events. And yeah, thank you so much.
And enjoy also there.
Yeah, thanks.
Thank you. Bye-bye.
Bye.